In today's Tech Exposed, we're going to do something a bit different. We're going to make an Arduino from scratch. After downloading the Arduino Eagle files from Arduino's official site, we sent the boards to be manufactured and purchased all the required parts from onlinecomponents.com. Now, if you have a large budget or have a high requirement for quality, you should get your boards assembled professionally. For many makers and even some small businesses, this is cost prohibitive, so we're going to try and do this on a shoestring budget. We recently acquired an incredibly cheap Chinese laser cutter, and using it and an overhead transparency, we're going to make a solder paste stencil. These laser cutters are extremely cheap, and it shows in their build quality, complete lack of safety systems, and barely usable software. However, using the cream layer from our Eagle file, we output an image that we were then able to import into the software. Then, through manual measurements and trial and error, scaled the image to the right size. We found that, by far, the best method was to fill in the holes in the image, instead of just having an outline of the holes. Then set the program to engrave, not cut. For our model, you need to manually control the laser power to make sure it's sufficient to cut through the plastic, but not cut through and engrave beneath the plastic. It's recommended to have some sort of ablative material beneath anyway, even though we don't. Doing this, we were surprised with the precision of the cuts and, while not perfect, works fairly well at making these small holes. Next, we need to line the stencil and the board up properly. Using some double-sided sticky tape, we tape the PCB onto a flat surface. We then place the transparency over the board, carefully lining it up with the holes. This is where you find whether or not you scaled the image properly in the laser cutter software. You can then duct tape the stencil down carefully on all four corners, holding it firmly in place. Try to pull it as tight as possible to reduce the tenting of the transparency over the board. Once it's secure, you can start applying the paste. As it is hard to get the paste back into the container, and solder paste is ridiculously expensive, I like to be pretty specific in the application. For this example, I was a little more liberal than I'd like, but hey, I was nervous doing this on camera. Then, using a simple putty scraper, try to push the solder paste into the holes and give the solder paste a flat top. This may take a couple swipes to get all of the holes filled, and probably even the application of a bit more solder paste. Now, we can actually place the parts of the Arduino. An Arduino Uno is a surprisingly simple board. Its key to success is in the simplicity of its interface, both hardware and software. First, we'll place the reset button, which is tied to the reset pin on the microcontroller, the ICSP programmer, and the reset pin in the headers. You'll also see why I didn't become a surgeon with my supremely shaky hands. Next is a ferrite chip inductor placed on the USB ground line to suppress high-frequency noise that may try and contaminate the overall ground for the board. Next is a diode, placed so that if the reset line for the USB microcontroller goes high, it will pull the harmful voltages down by conducting onto the 5-volt line. There are actually two varistors on the board attached to the two data lines of the USB, helping keep the lines clean from excess voltage without affecting the data signals. Between the two varistors is a 22 ohm resistor array, put in series with the data signals to act as termination resistors. A PTC, or resettable fuse, is placed in series with the incoming power for the USB to trip if the board pulls too much current, protecting your computer's USB. There is also a PMOS transistor here that works, via an op-amp, as an indicator to the board of whether power is being provided via USB or through the DC power jack. Next are a couple passives. Two of them are 22 puff caps for the crystal. A word of advice, some microcontrollers have these capacitors internally. However, if they don't, and you don't have them, your microcontroller won't work. We then move over a bit and place a capacitor to clean up the analog reference signal. A yellow LED, followed by another resistor array that acts as the current limiters for the LEDs on the board. Next is an Atmega 16U2 that acts as a USB to serial converter and makes it so that you can simply hook a USB up to the board without worrying about an FTDI cable. The QFN is also one of the more difficult parts to solder as the pads are tiny, and you need a very precise balance between enough solder paste to make the connection, but not so much that it'll bridge. The alignment, though, is relatively easy as it will self-adjust during reflow to line up on the pads more exactly. We then place a few more status LEDs and passives used for power conditioning. We then have a dual op-amp with one op-amp that acts as a buffer for a voltage divider that also controls the 3.3 volt LDO, and the other op-amp controls the communication status LED. Here's the LDO that accepts the 7 to 12 volt input via the barrel jack and drops it down to 5 volts. This is then followed directly by a small capacitor, and then another LDO that drops the 5 volts down to 3.3 volts, the one controlled by the op-amp. We then have another capacitor to clean up the power line, going directly to a 16 MHz ceramic resonator for the main microcontroller. you'll notice that this does not have the two external capacitors, as this resonator has internal capacitors. Also, as a ceramic resonator versus crystal oscillator, it isn't as precise, but is still quite small and inexpensive. Finally, on the other side of the board is an LED, resistor array, and protective diode to show the ICSP programming status and protect against transients on the power line. Another small power cleaning capacitor on the VCC pin of the microcontroller before moving to the two large electrolytic capacitors. The first I placed is to clean up the 5-volt power, while the second is to clean up the incoming power from the barrel jack. Both caps are rated to 25 volts and are completely interchangeable. The last surface mount device is a final diode to make sure that there isn't any current flow back into the barrel jack. We now very carefully put it into our cheap reflow oven, which, other than the awful smell it produces, works rather well. Obviously, it's important to place it carefully or else the parts will move. The solder paste holds them fairly well, but not perfectly. You can see the temperature profile on the screen, both what it is supposed to be and measured temperatures, with the graph clearly showing the 4 stages of the reflow process. Looking inside the oven is pretty interesting though. You can barely see the solder flowing and changing to become very shiny. Also, you can see the small passives moving a little bit as they get sucked onto the pads better, though sometimes this results in tombstoning or other issues. The larger devices, like those electrolytic capacitors, take more time to heat up and flow, but it is easier to see their large movement as well. Finally, not as part of the process, but just showing the effects of cheap materials, you can see the oven bed twisting in the heat, which for us isn't a big deal. After the cooldown period and the solder is solidified, the board is still too hot to touch, so be very careful. Now we're going to finish up with the through-hole devices, where you can once again see my shaky hands. First, we're going to put on the 16 MHz crystal that the USB to serial microcontroller uses. We then need to trim the leads off the whole thing, or it's going to sit weird while trying to finish it up. We then do the socket that the dip package microcontroller sits in, before moving to the headers. As you've probably noticed, the headers are 0.1 inches in pitch, but then they put odd gaps between some of the pins. Supposedly an accident that has continued through the years because they want to keep all the generations compatible. Finally, we drop the USB and the power connector on, and the project is complete. The time and effort to assemble a single board this way is non-trivial. However, it's a great way to learn more in depth about the electronics that are out there and get some practice with prototyping assembly techniques.